Okay, picture this. It's the year 2000. London is unveiling this absolutely stunning new piece of architecture for the Millennium, a super futuristic pedestrian bridge stretching right across the Thames. But what was supposed to be a symbol of the future, well, it quickly became famous for all the wrong reasons, and it sparked one of the great engineering mysteries of our time.
I mean, just look at it. It was designed to be a blade of light. Super sleek, a really shallow suspension bridge that was, let's be honest, as much a work of art as it was an engineering marvel. On opening day, thousands of people flocked to be the first to walk across it. You could just feel the excitement in the air.
But that excitement, it very quickly turned into confusion and then real concern. So June 10th, the bridge opens. Moments later, people start feeling this strange, really unnerving sway. And it just keeps growing, getting so bad that people are literally gripping the handrails to stay upright. And get this, just 2 days after its grand opening, this multi-million-dollar landmark was shut down. Indefinitely. The dream had become a total international embarrassment.
And so, the wobble mystery began. You had the world's top engineers just scratching their heads. They had accounted for all the usual forces, wind, the weight of the crowd, even that classic textbook problem of soldiers marching in step. But something else, some kind of unseen force, was at play here, and they had missed it completely.
And this is where we find this critical blind spot in the original design. See, engineers are amazing at planning for vertical loads. That's the downward force of gravity, right? The weight of people, the weight of the bridge itself. But the problem wasn't up and down. The mystery force was lateral. It was a sideways push that nobody saw coming.
So this became the central question. What invisible, sideways force was powerful enough to move a massive 320-meter steel structure like this? It wasn't the wind, it wasn't some flaw in the materials. The answer, as it turns out, was hiding in plain sight the entire time.
And the surprising culprit? Well, it wasn't an external force at all. It was the pedestrians themselves. The very people the bridge was built for were, without even knowing it, bringing it to its knees through this really bizarre phenomenon known as a human feedback loop. Now, the official scientific name to this is synchronous lateral excitation. Yeah, it's a total mouthful, I know, but the concept is fascinating. It's what happens when a crowd of people, without even trying, starts to walk in sync with the bridge's sideways movement. They end up feeding energy back into the wobble, making it worse and worse and worse. So here's how this dangerous feedback loop actually works. It all starts with a tiny, almost unnoticeable sway in the bridge. To keep your balance, you instinctively widen your stance a little and change your walking rhythm. But by doing that, your footsteps start to match the timing of the sway, and now you're pushing the bridge sideways with every step, which makes it sway more, which makes more people adjust their steps, and boom, you've got a powerful, ever-growing feedback loop. And here's the crazy part. It didn't take thousands of people to start this chain reaction. The engineers went back and calculated the exact tipping point. All it took was about 166 people walking on that bridge at the same time for the wobble to completely take over. Just 166 people. So how do you fix a problem like this? I mean, what do you do? Well, once they finally understood the cause, the engineers came up with this incredibly elegant solution. They realized they didn't need to make the bridge stronger or stiffer. They just needed to make it smarter. The core idea was just brilliant. Instead of fighting the force with tons more steel and concrete, which, by the way, would have totally ruined the bridge's sleek design, the goal was to simply absorb all that kinetic energy the pedestrians were creating. They just needed a way to bleed off that wobble energy before it could build up.
And the solution came in the form of these things called dampers. They retrofitted the bridge with 37 viscous dampers, which kind of work like the pistons in your car, and 52 tuned mass dampers, which are basically these big, heavy weights designed to move out of sync with the sway and cancel it out.
Really, you can just think of them as giant, sophisticated shock absorbers. Their entire job is to take that unwanted energy of motion, the wobble, and convert it into something completely harmless, tiny, imperceptible amounts of heat. The wobble literally gets turned into warmth and just disappears into the air. How cool is that?
You know, the Wobbly Bridge was so much more than just a PR nightmare. It was a massive wake-up call for the entire engineering world. This one failure fundamentally changed how engineers think about building these lightweight structures that people interact with.
So what's the key takeaway here? Ultimately, it's that people aren't just passive weight on a bridge. No, they're an active, reactive part of the whole structural system.
You have to account for this human-structure interaction. You have to model how a crowd behaves as a group, and most importantly, you can never, ever ignore those sideways forces.
And this isn't just a lesson for London. The principles they learned from the Millennium Bridge are now a standard part of engineering codes all over the world. So whether it's a new footbridge being built in Douala or a stadium in Yaoundé, the ghost of the Wobbly Bridge is there, making sure designers are planning for that invisible dance between people and the structures they walk on.
Which leaves us with a pretty fascinating final thought, right? The engineers back in 2000, they missed a fundamental instinctive human behavior. And it really makes you wonder, in our increasingly complex world, what other invisible human behaviors are we forgetting to design for? What's the next Wobbly Bridge just waiting to be discovered?